screen. Share, perfect. So there's momentum. Love momentum. Get that started. This is what happens when your computer restarts in the middle of class. All right, so conceptual problem number 4. Let's zoom in. There we go.
I went back to the what was it, the projectile chapter, and we only did like 2 problems.
Maybe you only did.
I was gonna say, that's what you not do only 2
I
problems.
always do all the problems.
All right, so we are. Okay, so if we look at this problem. Oh, don't look at the answer. Oh, you already saw it.
It's B.
I already have it.
C, wait, no,
B.
I think that says D.
I can't read well, so we'll see.
I can't read either, so.
How did you get a teaching?
Yeah. I don't need to know this.
You write amazing stories, though. I mean, Rolanda and her read guys.
I don't read. I struggle with reading.
All
right.
Gene and Sally were running thousands.
So if we check this problem, we already know the answer is B. Now, why is the answer B? A person stands under umbrella during a rain shower. A few minutes later, the raindrops turn to hail, though the number of drops hitting the umbrella per time and their speed remains the same. All right. Now, this one's a little tricky. Okay. Now, why is there more force?
Because the time is the same.
It's a solid.
The mass has nothing to do with this.
Really?
So, is that me or is that just blurry? It's a little. It just looks kind of blurry.
That's it.
That's better.
Oh, I think I got to put in this book. So
There we go.
that helps out a little bit. Yes.
Is it due to the hail transferring its energy into the umbrella in a shorter amount of time?
You're on the right track.
The water.
You're on the right track. So, if you look on an umbrella, not an artist either, but you know, there's my umbrella. Okay. When you have rain, rain just hits the umbrella, right? Hits the umbrella, rolls off. However, when you have hail, which one's better?
Left.
Oh
It's
man,
imperfect, which makes it perfect.
fair
It
enough.
shows humanity's eye and morals.
The right
All right.
was worse because
So, when a hail hits your umbrella, what happens?
It like
It
bounces
bounces
into it.
off.
It bounces. It bounces. So if we check this out, if we check our impulse force times time, which is also equal to the change in momentum, right? So my mass velocity final minus mass velocity initial. We already know that equation, right? Now, if we actually look at this, the key difference here is my final velocity. That's the key difference because here, when it rolls off, it's just going to be 0, right? The velocity hits that, it stops. When it hits the umbrella, it stops and then rolls off. So in rain, my final velocity is 0. However, we said hail bounces. So we don't know what it is. We don't know how fast it's coming down. We don't know that. But we do know it's going to bounce off the umbrella. So the final velocity is going to be greater than 0. All right, so let's give it a random number. I'm giving it 15. We'll go with 15. I like that. So if you have 15 times the mass, that's going to be greater than 0 times the mass. So this is going to increase the force because time is the same, right? Time. Which, if we increase force, that'll also increase the impulse. Does that make sense? So we're looking at bounce. Now tomorrow, you don't want your egg to bounce.
Huh?
Why not?
That's
Can we
a,
hard boil them? Is
Yeah,
that
can
what
I
No.
make it?
No. if it splatters, you're cleaning it up.
But if it's hard boiled and then covered in a bunch of stuff. then it
Yeah, why
can't
not just
crack.
hard boil it and then check to see if the shell broke at all, so then there's not as much cleanup.
Yeah.
So tomorrow during class, you want to
I'll
hard
bring a
boil.
tarp.
You want me to light up some Bunsen burners?
We can line them up ourselves. It's just the pain.
Guys, this classroom will stink for weeks.
Who cares? It's hard boiled eggs.
No, I care. I
All
care.
right.
Can
Now-
I soak mine in vinegar?
Yes.
That'll make it even more brittle.
It'll make it bouncy.
It'll make it brittle.
Now,
Exactly.
Wait, no,
Make it
doesn't it
more
just
of a-
take the shell off and then you just have that,
You have a thin layer of
that
like
membrane
shell.
there, and then you just go for it.
Sure.
No. No.
if you guys look at the next question, I don't have a slide for this, but if you look at it, what would you think?
Why is it just like close?
Wait, the bouncy ball.
Well, how big is the blob of clay?
The same size as the ball.
Oh yeah, no, blob is
No, it's the same
actually,
mass,
Never mind, same mass.
but the
It's
size
not
could
gonna
be
Because it
different.
bounces.
But the size could be different.
Yeah, the clay would stick.
The clay is
So-
directly, like, but it's smaller. so
With
it's gonna be-
impulse, we've been focusing on time. We've been focusing on time. So the force is going to be the same. Force is constant in this example. However, which will have the most time?
The bouncy ball.
The bouncy ball.
Because it'll smash.
It'll
and then it'll bounce.
It'll compress. All right. So the bouncy ball will have the most time in contact with the door. The more time, the more impulse. All right. So that's
How is
Is the clay hard or soft?
Yeah, because the
Yeah,
clay
if
just
it's a
stick
blob
to it.
of clay.
It's
it's
a
just
blob
gonna
of clay
stick to the
normally
floor.
isn't stick.
Yeah, like if it's
doesn't matter really, because if the blob of clay stuck, it would only have. Here's the door. It would only have the force going to it. It would not have the extra time that compresses the ball, compress, going back. It's still in contact with the door until right like this. So either way, it has the same. Yeah, it's gonna have more time. All right. Now, looking at graphs. Love graphs. Beautiful stuff.
Grass.
What?
I thought you said grass. I was like,
Grass is good too.
How green is it?
All right. Now, when we check out graphs, force times time graph, all right, we looked at graphs similar to this. All right, we looked at distance time, velocity time, and acceleration over time. But if we look at a force time graph, to find the impulse, you have to find the area. Okay? Not too bad. This is probably the easiest part on the chapter. You have to find the area, okay, of each vector and then line or add them up. Okay, so by taking the area under the force time graph, we found both the impulse and change of momentum. If the force is not constant, the area can be found by breaking into solvable shapes and summing them up. Okay. So, all right, so if you look at the next example, example number 7, we have to find the area that is under the force time graph. All right, so checking this out. I'm gonna zoom in a lot. We gotta find the area. Okay? There we go. So I'm gonna label this triangle 1. All right. So to find triangle 1, all right, what's my area equation? 1/2 BH, perfect. So my base is 1. My height is 6. So 1/2 times 1 times 6 equals 3. So area 1 is 3. Let's check out my squared, well, that's going to be a rectangle. Rectangle number 2. All right, so all you got to do is base times height. So my base is 2. I gotta zoom out a little bit. So my base is 2 times my height is, well, 0 to 6, which is equal to 12. All right, so let's look at another triangle. So our triangle is 1/2 base times height. My base from 3 to 5 would be 2. What's the height of the triangle? Well, that's still 6. So what would that equal? Perfect. And then the last one, triangle 4. Okay, 1/2 the base. The base of the triangle 5 to 7 would be 2. Times the height. Now I go down 2, right? So from here to here, it's actually -2. Okay? So if you combine all those, that equals -2. Does that make sense? Just got to find the area. All right. Then, after finding the area, you just got to combine them all. So I have 3, 12, 6, -2. Combine all those. 15, 21, 19. That's your answer. Impulse, kilogram meters per second. Oh, right. Okay. Now, number 8, a 5 kilogram object with an initial velocity of 3 meters per second. Okay, so here, what you're going to have to do, a 5 kilogram object with initial velocity of 3 meters per second experiences a force shown in the graph. What's its velocity at 6 seconds? This is a tough problem. You know, like, this is a tough problem. But if we think about it, all right, so we know impulse is equal to our change in momentum. So mass final velocity minus mass initial velocity, right? So my mass in both of these, impulse, is equal to 5. I have to solve for final velocity, minus 5, and my initial velocity is 3. I got that from the problem. It said my initial velocity is 3. Now, it says, what is my velocity at 6 seconds? So at 6 seconds is right there, okay? So looking at my graph, I'm going to zoom in. So 6 seconds, right there, okay? So really, I'm not worried about anything over here. I'm worried about what happened to get me to 6 seconds. So can I solve for my impulse? Yeah. Gotta find the area under the curve. So solve for impulse here, and then plug it in to here so that we can solve for our final velocity. Okay. So what you guys got? Okay. So when you solve for impulse, you had a triangle shape and a rectangle shape. So the triangle is half base times height. I got 45. For the rectangle, base times height, I got 90. So you got to combine both of those because that's the total impulse. So the total impulse is 135. So what I did was I plugged 135 into my impulse and solved for velocity final. How we doing? You guys are very quiet. Fair enough. I'm just checking, making sure you guys are getting this. This is our last day of impulse. Okay? I mean, we'll cover it in other problems, but all right. So, one last problem. One last problem. Oh. No, you didn't. All right. So, two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. If the mass of canoe 1 and its occupants is 130, and mass of canoe 2 and its occupants are 250, find the velocity of each canoe. Each canoe moves after 1.2 seconds of pushing. Okay. So, if you look at our diagram here, the force, so person in boat 1 pushes with a force of 46 newtons. However, 46 newtons is pushing backwards towards them, right? So that's going to be negative 46. Okay, just a heads up. So when we set this up, I'm just going to start it. All right, I want you guys to do the rest on this last problem. All right, so when we start it, we know that our impulse is equal to force times time, which is equal to our mass times velocity minus initial velocity. So it says find the velocity after each canoe moves 1.2 seconds. So let's find canoe 1. So canoe 1, that was the guy pushing, right? So the force was pushing back 46 newtons, right? Where canoe 2 was moving forwards. So our force is negative 46. Our time was 1.2. Our mass. So we're doing canoe 1. So canoe 1 had a mass of 130. It said, what's its final velocity? Minus 130. What's its initial velocity? 0. Right? 0. And that's how you're going to set it up. Okay? You're going to do the same thing for boat 2. Okay? Boat, and question B. Just making a prediction. What do you think? All right. Try it out. Try it out. Yes, you already got an answer.
No, I was just what
Oh, it's not
is the day that music died day? What is that?
The day the music died, we're singing bye bye, Miss America.
Oh,
bye.
that one. Okay. Yeah.
Drove the Chevy to the levee, but the levee was dry.
Aren't you a choir teacher?
Oh, I can't sing worth I have a terrible singing voice.
Yeah, we just started
My
start a record.
wife's told me I'm a bad singer, so
That's so
Oh my word.
she's honest with me. I don't care.
brutally honest.
One time Mr. Porter sang like a 5-minute song to
Oh
our
my
class,
God.
and we just like sat
that's
there and
fantastic.
That's
laughed.
Mr. Porter,
He
man.
gets so far into like some of his characters that he does when he reads us, like he reads like the
When he
like,
reads
plays
them.
or
When we were reading The Crucible, it was intense.
Oh my
You
god.
could feel the room shake with Mr. Reverend Hale going.
Yeah.
It's
I had a
negative
cold too, so it was like.
0.42 and positive 0.22.
So for boat 1, you got negative 0.42, and then you said for boat 2, 0.22.
Yes.
Okay. So which do you think is going to have more momentum?
Normal, the second row,
Okay.
because it had the force.
Let's say second boat.
Normal.
That's our guess. Now let's find out. So momentum is mass times velocity, right? So for boat 1 has a mass of, I lost it, 130 times the velocity you just said. So boat 1 had a negative 0.42, where boat 2 had a mass of 250, times that by its velocity, 0.22.
You see speech?
So hopefully what you actually saw was the momentum's the same, just opposite directions. So hopefully you got negative 55 and you got 55.
Oh, no.
With sig figs, yeah.
No, without sig figs.
Really? It's like,
It should be the same.
Mine said 54.6.
mine did too.
It's because you rounded for like the other. Yeah.
So they should be the same, just opposite directions. Now, what is the momentum before they got pushed? Zero. They're not moving. Right? All right, tomorrow we will do our egg drop. All right? Yep. All right. Guys, I hope you have a fantastic day. Hopefully it's starting to make sense a little bit. Have a good one. You too. We'll see ya.
Yeah. We're going to go.
Have a good day, guys.
But I want to put it in a box. That's probably not an option, but put it in a bag with a bunch of straws.
Get the AR.
Okay. Have a good day.